We're starting a new chapter. The second unit is going to contain a little bit of chapter 3, which is basically just enough to cover the determinants up through Kramer's rule, which is a really, really important section. And then we'll move on to chapter 4. Chapter 4 we're going to spend a good amount of time in, and that's going to be probably for the engineering people in here the most difficult chapter, for the reason that it's entirely kind of theoretical. It's going to be more abstract. We're going to reason more with proof writing. We're going to reason more with what it means to think in terms of definitions and axioms, propositions, and so on and so forth. It's a different kind of thinking, and once you get in the rhythm of thinking that way, you'll unlock the chapter as you review for the unit exam. And then chapter 5, we're going to start, we'll shift back into a slightly more computationally oriented thing with eigenvectors, eigenvalues, things like that. So that's kind of the preview all the way up from now to after the spring break, and then I timed it when I organized the calendar so that the exam's happening after you return from the break, so that's giving you not only if you got behind and need to catch up on topics, you have that entire spring break week to do any necessary catching up, study, review. I'll make sure I get you hopefully that exam review before you leave for break so that you know how to study, just get prepared for the return. Does that make sense? Roughly speaking, what you should budget for with your time, what you should anticipate the difficulty roughly of the class is going to be. It ramps up a little bit, and then the third unit, depending on how comfortable you are with the first two, will be either really easy or not. So do yourself a favor in this unit and make sure that the work you do will make sure you set yourself up for a really easy coast in that last unit. Okay, so I already threw this definition out just because it's long. And yes, write it down, but what we're going to do really more importantly than just this definition is the algorithm. The algorithm is very straightforward. I coincidentally, I've been teaching like this 12-year-old kid linear algebra for the past semester. And he was able to figure it out in like 20 minutes, okay? So I'm not too concerned about this section because it's just an algorithm and it's just point and shoot. And if you understand how to do it visually, you're fine. And then what's going to happen is I'm going to record something on 3.2 later today and also make sure that's on the YouTube. And that's going to basically say we can do the general computation. Now there are shortcuts to speed up the process because we're not always going to have conveniently small 3x3, 4x4, 5x5 determinants. So let's do an example. So actually, I'll read this. So for n is greater than or equal to 2, that's just to make sure that we don't have a matrix that is just a 1x1. The determinant of an n by n matrix, A is equal to ij, A is equal to A sub ij, is the sum of n terms of the form, and we have this alternating sign business, so plus minus A sub 1j, determinant big A sub 1j. These indices will always match each other, by the way, with plus and minus signs alternating. The entries, we start with a positive, and then it'll go to negative, etc. These entries, A11, A12, A1n, this is what's being indexed by this idea of A1j. These are from the first row of A. So whenever we talked about the addresses in a matrix, about A sub ij, the I was the number for the row, and the j was the address for the column. That is all going to maintain exactly the same, so you don't have to learn anything new there. So in symbols, if I want to compute this determinant in general, we did 2x2 determinants through a formula, but now this is going to be any square matrix that is greater than or equal to 2. A11, determinant A11, and if I'm crawling across the top row of a matrix, then I'm in row 1 still, so that first index is 1, but now the column number is going to increment upward all the way up until I get to the last column. I'm alternating sign, so the way we do that with summation notation is we take negative 1 and raise it to the necessary power so that it's flipping on the appropriate one, and then we can just discretely do this sum like this. So j is 1 to n, sum of all this. Now, what is this the big A sub ij? Well, what's going to be is you take your original matrix A, and you're going to cover up. You can think of it either as covering up or just eliminating, whatever is easier for your to conceptualize. You'll just entirely delete the ith row of the original matrix, and then also you'll just delete the jth column of the original matrix A. So for whenever you see one of these A sub ij, so like A12, what this one right here means is I took my original matrix A, I delete the very first row because the 1 is in the row place. And then since 2 is in the column spot, I'm just going to delete the second column. And then anything that's left over, you maintain its relative position to each other. That forms a smaller matrix, and that's going to be what we mean by the A sub ij. Does that make sense? So that's all of the anatomy. Let's do an example, because the example makes this seem way less complicated than it looks in words. Here's an example. I thought I forgot to press record for a second. Okay, so we were going to compute the determinant of this matrix. So here's A, and let's do a 3 by 3. So 1, 2, 0, 5, 4, minus 2, 0, minus 1, 0. Okay, quick word on notation. If I'm presenting to you just the matrix itself, we're going to do the notation that we've been all this entire time. What you're going to start seeing as a shorthand is, I'll put this here as a notational thing, because I may interchange it to get you used to just switching in your brain which one is which. So if I want to signify that I'm actually doing a computation of the determinant of A, what I can do as a shorthand is I can reproduce the actual matrix itself, but instead of doing the typical, hard brackets, I actually just do a solid line. Just a straight up and down line with no notch in it, and then reproduce the contents that I'm trying to compute the determinant of. Okay, so that's just a quick word on notation. So irrespective of the size of the matrix, this is always just going to be a convention. That if I write down, or if you see and read determinant of a matrix A, and you're provided with what those entries are, then you can think of it computationally as just putting those flat lines instead of the brackets. And likewise, if you see just these flat lines around the matrix, and you name the matrix inside, you could write that shorthand as just the determinant of it. So it's back and forth, doesn't have any meaning aside from just notation. Okay, is that clear? Okay, it's actually computed. Let's do this definitionally, because that's how we want to learn math. You want to learn concepts by definition and then an example and application. And as you progress through, theorems then become the tricks, the shortcuts, the conclusions, the patterns, things like that. So determinant of A. What does the definition say? Well, it should be this sum. And I should be alternating the sign on this particular sum. I want to take A11, the determinant of big A11, and then I'll go all the way across the row. And so how many rows do I have in a 3 by 3 matrix?
3.
I misspoke. I meant to say columns, go across the columns. But it's the same thing. We are 3 by 3. So I'm going to start with A11 times the determinant of big A11 here. And since I'm alternating sign, I'm going to go to minus. And then what's the next one going to be? Well, I'm still in row 1. That's the key here. Right now, the way that this is defined is that we just go across the top row. But now, which column am I going to go to?
2.
Yeah, the second column. So now it's A12 times the determinant of big A12. Again, for ease of just practice, these are always going to match each other in index. Okay, so I need to not forget to alternate my sign back to positive for my third column. What's it going to look like? I have A sub, what's the row?
1.
And the column?
3.
So then determinant of what?
A1.
A12. Okay. What I'm demonstrating in this example is not necessarily what you have to do for every time you compute this. The idea is, once you understand how the pattern works, you can shorthand this a lot. But I'm showing you the full expansion from the definition so that you can see exactly why every computation is done the way it's being done, okay? So now, let's actually piece these pieces together. A11, the entry that is positioned in which row and which column?
First row, first column.
Okay, first row, first column. So which one is that?
1.
1. So I have 1 times the determinant of, and I'll use my shorthand here, the determinant, so I'm just calling a determinant with that bar. What is big A11? So recall that I can construct a big A sub ij by deleting the ith row and deleting the jth column. So let's go to my matrix originally, A. What happens if I delete the first row and the first column? If I delete this entire first row and I delete this entire first column, and if you've got it on your page, you can use your fingers to block up the rows and the columns. What's left?
Or negative 2 by 2.
Yeah. And so that becomes what we mean by that smaller A sub 1, And then, since I want the determinant of it, I'm just kind of shorthanding into this determinant notation. Any questions about how I knew what to plug in for this entry?
First row, first column.
Any questions about how I knew what on earth to substitute for this A11? And then any questions about why I'm notating it like this for the determinant? Okay. So then I'm alternating my sign minus, what's A12 in this case, the little A12?
5.
Yeah, 5. Because think about it, like once I'm doing this determinant, I've kind of mentally just told myself I'm going across this top row. So I'll just skim those items. So 5, what's the determinant? A sub 12.
0, negative 1, 0.
Yeah, so I'm covering up, that's still covered up, but now I'm deleting the second column. So the second column's gone, and I have a 2, 0, skip over the middle, and minus 1, 0. Okay, and then I alternate my sign back. What's the entry A13?
0.
0. And then the smaller matrix, submatrix A sub 13 is
2, 0, 4,
good, yeah, because I take this, I delete it. I take this, I delete it. So all that's left is 2, 0, 4, minus 2. Quick observations that's going to be helpful to extrapolate. What's the original size of A?
3 by 3.
What's the size of these submatrices?
2 by 2.
In other words, we take the original size of the matrix, and when you really think about how that's been defined, it will, no matter what original size you had, these we expect to always be just one dimension lower as a square. So if this would have been a 17 by 17 matrix A, all of these would be 16 by 16, just one less. And so why do we care about being able to increment one less and one less and one less? It's because we actually memorized the formula for the 2 by 2 determinant. So we know what to do by the time we actually get to 2 by 2s. And so the general strategy is, irrespective of what original size you had to begin with, you'll just keep peeling away the onion layers over and over and over and over as many times as you need until you finally get something in terms of just your 2 by 2. Yes?
Does this only work for square matrices?
Yes. That's going to be a big thing. When we're talking about these determinants, it's going to be n by n. So in general, you can make that assumption we're talking about n by n. Very good question, yes. So don't worry about determinant stuff if you got like a 7 by 4. It's just not defined. Okay. And how do I know that? Well, because when I actually go to my definition of determinant, it's actually locking in and specifying that there is no meaning of determinant outside of my n by n. Okay. So since we know what the formula is for these 2 by 2s, I'm really just multiplying 1 by 4 times 0, and then I'm subtracting away the product of these. So minus 1 times minus 2, minus 1 times minus 2. I then have minus 5, 2 times 0, and then I'm subtracting away then this one, minus 1 times 0. And then plus, do I really care about even expanding this?
No.
Why not?
0.
It's going to get knocked away to 0 anyways. Keep that in mind. That's going to become a major motivation for most of the strategies we take on for the rest of the section, okay? The convenience of having a 0 as one of these entries is going to be huge, okay? So keep that in mind. And then this is just arithmetic at this point. That's 0. This is positive 2, but it's minus. So 1 times minus 2. And then 0 and 0 makes 0. And if I take 0 and multiply it by 5, it doesn't matter. So we have negative 2 is my determinant. Okay. Do we have any questions about how we actually define what we mean by a determinant.
Why do we only go through the first row?
That's a very good question. The answer is, that's the definition. The theorem in expansion is that we ask exactly that question. What if the top row isn't the easiest way to go? What if it's easier to go through, say, honestly, it's easier to go through this third row if you think about it, because how many zeros are we going to encounter? So we really only have to worry about one computation. Okay, so fantastic insight, because that is precisely what motivates the rest of this section. Is something we're going to call cofactor expansion, which says not only do we have the flexibility to choose which row I choose to skim across, we could actually choose to skim down a column, and then the column is also going to pan out. So keep that in mind when we put up the next theorem, okay?
So we would want to choose the bottom and right column, the bottom row and right column.
I'm not gonna lie, I'm really lazy. I would choose going down this. I would go down the third column because that's a 0 and I get 2 zeros. So I wouldn't even. That's like having a 0 here and a 0 here. So I wouldn't even need to compute 2 of these determinants. And then that makes the only determinant I'm computing times -1, which means I just need to figure out this determinant out and put a minus sign in front of it. So convenience is going to become the algorithm here.
The minus would cancel out, right?
Well, yeah, so it depends. That's a good observation, because if I'm alternating signs, then minus would alternate with the minus.
So just do the determinant.
But I just speak more generally because if I have a larger, if I started with a larger matrix to begin with, I don't know how many times I'd have to change signs or peel out anything that gets smaller and smaller. Okay, but yeah, let me write down the next little thing here, because it'll be much faster. How many of you remember when you took Calc 1 and you got shown like the whole limit definition of a derivative, and you had to show through the whole annoying, obnoxious process that the derivative of x squared is in fact 2x after you do all this absolutely horrendous algebra, okay? So it's not that that's wrong, but it definitely motivates the question, well, gee, there has to be an easier way to do this. There has to be a better pattern to follow. And that's precisely what we do in most of mathematics, is we get the base definition to start and say, okay, that was horrible. Certainly. There has to be something better. There has to be something more convenient for computation. And there is. So let's define what we're going to call the ij cofactor. So given a matrix A, which takes A sub ij, this is what we're going to call it, ij cofactor of the matrix A, so of is the number capital C sub ij given by, and then this is its definition. So if you ever need to remember what these capital C's mean in your textbook or Pearson, this is how it's formally defined. We take -1 and we're going to alternate the sign according to this I plus j, okay? And then we multiply it by the determinant of the submatrix A sub ij. Again, this is indicating exactly the same thing. We haven't changed. What's really the only difference between this C sub ij and before with the definition? Well, we're not tagging along that entry A, okay? And that's the main thing to be aware of, is that we're accommodating the sign change and the determinant of the submatrix in this cofactor. So how can we apply it? Let's define what I mean by, I use the term, so I'll define it more explicitly here. The formula, because, well, actually, before I write that out, I'm going to re-express this. Do you guys have the computation in your notes? So I'd be okay to erase the number part?
Yeah.
Okay. Okay, so in light of this ij cofactor, let's actually see if we can re-express this exact example using this cofactor notation. So the A11 is still here, and it's positive, and it is with this determinant A11. So I would say that this is A11 times my ij cofactor C11. Now here's the thing. The Cij has already accommodated for me my sign change. So instead of subtracting, I actually can just add together these linear combination. So I have now A12, C12. Notice it's plus even though it needs to alternate sign. It's because, look at the index. The index is 1 and 2. What's 1 plus 2? Odd power. It's going to remain negative. So this is accommodating the indices in the way that we define an ij cofactor accommodates for our sign changes. So when you use your cofactors, just put plus between everything because your indices will take care of that. And then the last one would be plus A13, C13. Okay? So this is a much easier way to view these expansions. Okay, so this formula, whenever we take a determinant, this is an example of what we're going to define here. So this formula, the determinant, I'll make a new line for it actually. Right. So determinant A is equal to A11 C11 plus A12 C12, etc. to what? A1n C1n is called a cofactor expansion. Across row 1 of A. So we're defining cofactor expansion across the first row of A. Suppose I had, instead of going across row 1, done A21, C21, A22, C22, all the way down to A2n, C2n. Well then, that'd be a cofactor expansion across row 2. So on and so forth. So if I put in something general like an I, you could generalize this definition to A sub I1, C sub I1, blah, 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 for row I of A. Okay. So the reason we do this is because I can now do compute determinants by doing cofactor expansions down any row or any column. Check the time. Okay. So the determinant of an n by n matrix A can be computed by a cofactor expansion across any row. Or down any column. Whatever is going to be easier in context of your matrix. So the expansion across your ith row, or notated with this notation, row I of A, is this. So I would say that my determinant A, the formula that I would be plugging it down is I would start with A, my row number is I, column 1, CI1, and then I just progress. I keep my row number fixed, and then I just increment and move down the column list. So CI2, that's going to go on and on until I run out of columns, which will happen when I get to the nth column. CIN. Yes for the across a row I. This notation, you can read this. Questions about reading this? And then now let's do it for the columns. So then the cofactor expansion down. We're now going to generalize the column, so the jth. I could put this as col j, so I keep my notations parallel. So column j of A. Don't need the word the, so down column j of A is, so it's going to be very, very similar in construction. Determinant A. Now, I need to, the row is going to be the thing that changes. So I'll start with the top row because I'm going to be going down the column entries. And I'll start with the first column. So I'll put J there. C1J. So I've chosen to go down column J, and that's going to be. So notice how the I's were fixed because we fixed the row. Now the J's are fixed because we're fixing a column. Plus, and then the thing that varies is the row number. So I'm going to go to the second row now, staying in the jth column, to J, so on and so forth. I go all the way down to the nth row, because that's the last one, still stuck in the J column, and J. So we'll be able to kind of, if we understand this one, make it apply to the column version. Questions about any notational related stuff? Because I know that there's a lot of different symbols here. Okay, we ready to just see how it works on a matrix?
Yes.
Okay, let's do it. Now, I'm going to make a disclaimer quickly. So long as your arithmetic is good and you follow the rules of your cofactor expansion, for all of these determinants, there's going to exist a ton of different ways that you could solve any of these. So choose the one that's going to be most convenient for you. That being said, some matrices will just have an objectively fastest solution. And so you're going to tend to want to do those. But you don't have to if you want to get to the same correct answer. It's just an issue of convenience, okay? So if there's any question about how to know which was the right column, how to know which is the right row, the answer is there's really no right row and there is no right column. It's entirely up to how much arithmetic you want to be stuck doing and how much scratch paper you want to burn through. That's pretty much the only difference. So you will always end up at the same correct answer if you follow all the rules and compute everything correctly, okay? So that's the disclaimer. You don't have to do it the way I do it, but on an exam when you're pressed for time, let's maybe not do the most inefficient way to do it and go for the efficient way to do it, all right? So let's do the determinant of 5-0 minus 0, 5-0 minus 5-0 minus 7, 3, minus 8, 5, 2, 0, 0, 0, 2, minus 4, 3, minus 6. Now, when I look at this matrix and I'm thinking I'm going to compute this determinant, my brain immediately goes to how lazy can I possibly be to get to the correct answer without having to actually work that hard? And so any consecutive strings of zeros, rows and columns that have a high volume of zeros, that's going to be really fun. Because, as we did that previous example, that zero just kind of eliminated having to multiply out whatever that other determinant was. So if I just used the basic starter definition that was originally on the whiteboard at the very beginning of the lecture and just go across the top row, you would have to do 5 times the determinant of the 3 by 3, minus 7, the determinant of another 3 by 3, 2, determinant of the 3 by 3, 2, determinant of a 3 by 3, and then for each one of those 3 by 3s, have to then go through and then get it down to 2 by 2. That's a lot of work. Okay, so I don't want to choose that. This looks tempting as a row because there's 2 zeros. But what's nice about cofactor is we're not trapped on just rows. We can take columns too. This is really sweet because I really am just doing the 2 times the determinant plus 0 plus 0 plus 0. So do I really care what the corresponding submatrices are for these? No, it's just going to go to 0. So I can think of this as just 2 times the determinant of then its corresponding submatrix, right? So what's the size of this matrix right now? So I can anticipate my submatrix being what size?
2 by
Right,
3.
just decrease it by one. So we got to think now about which entry. So 2 is right here. We're going to cover up 2's row, and then we're going to cover up 2's column. So imagine this column's gone, and imagine that top row is gone. And the remaining entries are going to be, actually, I can just eliminate these. So imagine you cover up delete that first row, delete that second, or the third column, and then all that's left is 0 minus 5, 0, 3 minus 8, 5, minus 4, 3 minus 6. So, since I already know that those are zeros, I effectively can leave this, but what's happening is plus 0 plus 0 plus 0. Equals 3. Okay. We have a new determinant. So kind of mentally reset each time you hit a new determinant and then optimize it. Okay. Yeah, this is really nice. I could just drop down and hit 2 zeros. So I'm really still only computing one determinant. So I have this 2 hanging on the outside. Quick notational thing for when you're handwriting your work, because this will mess some of you up later. Make sure you separate out your order of operations and stuff. 2 times this entire object, the determinant. So I'm going to use hard brackets not to indicate a matrix, but to indicate that all the computation that's going on in here is with the determinant, and this 2 is hanging on the outside. Okay. So then I'm going to go down. I have 0. And then now I'm going to alternate the sign. So it's plus 0, negative. What's the next entry in this column? Okay, so I'm going to put my negative 5 in. Times the determinant of the, so this, what size is this one?
2 by 2.
Well, right, the submatrix is going to be 2 by 2 because the size of this is 3 by 3 right now. So then if I remove the top row and I remove the first column, then I'm going to have minus 8, 5, 3, and minus 6. And then
No.
we alternate the sign.
You want to remove.
Oh wait, sorry, yeah, no, I just completely delete that. We're removing the row with the 5 and the minus 5 in it. So we're removing this row, and then we're removing this column.
Yeah.
So I've got 3, 5, minus 4, minus. Thank you, Dr. Arthur. I'd be like, that's not the answer. Okay. And then plus 0, right? We alternate sign, but it's just 0. So then I think about this. I have this positive 5, and I can multiply that constant out here with 2 for 10. And then that's just 2 by 2. We finally got to what we know how to compute directly. So 3 times minus 6 is negative 18. And then subtract negative 4 times 5, which is negative 20. This is just a side note. Look how careful I am with the way I do my order of operations in parentheses and subtracting negatives, okay? I do that because you have all seen probably 18 times this class. I mess up arithmetic all the time, okay? So when you're doing your own work and you don't want Pearson to yell at you because it can't discern where the arithmetic mistake happened, just be careful with the sign changes. So you get 20 minus 18 is 2, so this is 2 times 10. So in reality, we really only computed, one determinant, actually. Because everything else was able to be zeroed out. That's not always going to happen. But when it does, take advantage of it. Okay, to clarify, in case anyone doesn't want to ask the question, but secretly wants to, how do I know that this is this? It's because -5 is the corresponding entry. So I look at this entry, and I'm going to delete its corresponding column and its corresponding row. And then everything that's left over is how I can know for sure what to put there in the next one. Questions about this example?
Why is it 0 minus -5 again?
Good question. Remember that, well, I'll answer this two ways. A, we are always going to alternate signs. So the easy intuitive way is, since I started positive, the next term is going to be subtracted, and then we're going to go back to addition. The definitional answer is that what's really happening is I'm taking the ij cofactor for this specific thing. So think about where -5 is at. The address of -5 is in, so that entry right there. So that -5 is the entry in the second row and first column.
Okay.
And then that means I'm interested in the ij cofactor C21. And by definition of what C is, if you look at that in your notes, actually I'll put it over here. C21 is going to be -1 to the I plus j times the determinant of the matrix A sub ij. What's 2 plus 1?
3.
And so -1 raised to an odd power, it's gonna be negative. It'll flip to negative. So I need to make sure that I have this negative value for this determinant. So I need this to be overall negative. There's two ways to think about it. You can either keep track of how you've alternated the signs, or you can directly just double check and hand compute from the definition of an ij cofactor and double check, am I flipped to an even power or am I flipped to an odd power? That's a good question. Any other clarifying questions for the computation? Okay. Then I'm going to show you one more very special type of computation which will motivate 3.2 with, oh, we're doing good, okay. The following question I'm about to put on the board is, I really like it. Maybe not for the exam, but exam type question because it's more conceptually oriented instead of just brute force. Alpha 0, 0, 0, 0, 1, beta 0, 0, 0, 1, 2, gamma 0, 0, 1, 2, 3, delta 0, 1, 2, 3, 4, epsilon. Okay, what's the size?
5 by 5.
It's a 5 by 5. What type of matrix is this?
It's a lower.
It's an upper triangular matrix. Another word we could use for this is basically an echelon form. Okay? So keep that in mind. Foreshadowing. That's really helpful in the next section. Okay, so let's see what happens if we take this really, really special, type of matrix. I mean, upper triangular matrices, or just triangular matrices in general. So remember the whole motivation of let's just farm all the zeros together. So let's drop down this first column and take it. So I've got alpha times the submatrix that's what's left. So I get rid of this entire first row, I get rid of this entire first column. So I'm left with the 4 by 4, beta 0, 0, 0, 2 gamma 0, 0, 2, 3 delta 0, 2, 3, 4 epsilon. And minus 0, plus 0, minus 0, plus 0, all equals 0. So I can just leave it as it is. Okay, so next. This alpha is just hanging out for the ride, and then now let's pretend like this is a completely fresh problem, okay? If this was the original problem, well, I mean, the logic's still the same. There's a whole string of zeros for me to take advantage of here. So let's drop down this first column. So I'll take the beta and then now the corresponding submatrix, right? So I remove the first row, and I remove that first column. I've got gamma, 0, 0, 3 delta 0, 3, 4 epsilon, minus 0, plus 0, minus 0 is all 0. Let's do it again. Alpha times beta, and then now I'm going to do my gamma. Same thing, I'm just going to take the first column, gamma, times, so I cover up the first row, because that's where gamma is at, delete that first column. All that's left is this 2 by 2, delta 0, 4 epsilon. But what do we know about the formula for this? It's going to be delta times epsilon minus 4 times 0. 4 times 0 is a 0. So the answer is alpha, beta, gamma, delta, epsilon. Why might that be particularly a fascinating result in light of the original matrix? Did any of those other upper entries really matter?
No.
What's the only thing that affected this determinant? The main diagonal. One could even say that the determinant of this triangular matrix was just a product of its diagonal entries. Is that always going to happen? Yes. Short answer, long answer short. The answer is yes. And we call it, we put this in a theorem. So this is probably one of the more important theorems of this section just because of its usefulness. Now because here's why. Not every matrix that you get is going to come in a nice prepackaged echelon form for you, okay? What do you know how to do to take any matrix and make it? Row reduction. Which means that, say you have a 10 by 10 matrix, and you can row reduce it. You don't even need to get it into reduced echelon form. You just need an echelon form. As soon as you get that square matrix into an echelon form, bingo, every determinant calculation is basically done. You just march down the diagonal. Okay, so we've opened the door to a ton of new problems we can solve with this. So I'll write down the theorem so you have it in your notes. Because technically, this would have worked symmetrically if this would have been a lower triangular. We happen to not care as much about the lower triangular because when you do the row reduction algorithm, we go for the upper triangular anyway. But it does technically work for both. So if A is a triangular matrix, then we have found that computing this determinant of A is just taking the product of the diagonal entries. So is the product of the entries on the main diagonal. Of your original matrix A. Okay. Something I want to point out here, okay? I'm going to teach you how to do some more mature mathematics, okay? How to learn mathematics at a higher level beyond just what you maybe have been doing, okay? So when I read this theorem, I'm not just going to memorize this theorem. Let's think about some of the ramifications of this. So if I just take that product of all of the diagonal entries, okay, what if one of those diagonal entries is 0? Say any one of these alpha, beta, gamma, delta, epsilon, any one of those being 0 does what to the overall determinant automatically?
0.
Boom. Gone. Okay? Now, if you imagine taking a square matrix and shoving a 0 where there should be a pivot, what does that introduce to my system? Free variable. Okay, well, interesting. That's a problem. So we lose our uniqueness of solution. We suddenly have a free variable. And what did we know about the existence of a free variable when talking about whether we can even find an inverse?
We
forming. We can't. The moment you throw in that degree of freedom, boom, it's over. It's not invertible, okay? So if I think about this, knowing that any one of these could have been 0 means any one of these could have made a free variable here, meaning that any one of those being 0 makes this not invertible. And so what we're going to find in the next section is that the determinant if the determinant of your matrix ends up being 0, then it can't have an inverse. Because we're going to see that doing these elementary row operations is only going to, very predictably to certain rules that you'll memorize, influence the output of a determinant. So for example, if I multiply a row and then replace, row replacement doesn't change the determinant value. So if I had some matrix A, and I did a row, not a swap, but just a replacement, so I scale a row and I multiply it, and then I generate essentially a new matrix, right? That's row equivalent. Then, so long as I didn't swap out 2 rows, and it was just a row replacement, the determinants are still going to be the same thing. Now, what happens if I decide to make 2 rows swap places? The only difference then is that I negate the previous determinant. So if I swap the row, now the determinants are the same magnitude, I just need to put a minus sign in front of it. Okay? So when I take a general matrix, and then I row reduce it to an echelon form for the reason that that's super easy to compute, I really just need to keep track of how many times I needed to swap rows to see whether or not I need to multiply the result by minus 1. Because if I can row reduce a matrix and figure out it has a free variable, what can I automatically compute the determinant to be? 0. Okay? So all of that comes from an innocent little theorem, all of which came from a remarkably innocent example, all of which came from a very, very innocent exploration of making your life easier when following a definition. A definition which was inspired entirely by wanting an easier life from the first definition. So do you see how these sections are telling many stories? And that you can learn vast volumes of mathematics by following basically the nose of the lazy person through a definition and all of the ramifications. Because then that nose of a lazy person finds the brilliant stuff, the theorems, the shortcuts, okay? So internalize this as much as you can. I'm going to record 3.2 independently. I didn't want to waste an entire lecture period because it's literally just 1 page of notes with an example on there, okay? So it'll probably be just like a little 22-minute thing that I record on top of this lecture, and I'll upload it to the playlist so that, watch that so you can come prepared for applying it to solving systems of equations for Cramer's rule on Wednesday. If they choose to cancel class, we have too much to get through anyway, so I will just find a way to record it and still put it on YouTube so that you have it on Wednesday, okay? All right. You guys can go early again. Woo!